Good day, Calc students. Today we're going to go over a little more integration stuff, but what we're going over today are called improper integrals. Right? We have things such as improper fractions, where the numerator ends up being larger than the denominator, and that's okay to work with. We can go ahead and do those. But we also have things that are called improper integrals as well. And what improper integrals are, let's pop those there. Improper integrals are things that have some form of what we would call a discontinuity in them. Things that are continuous have a definite answer, and we can certainly find those. So if something is discontinuous, that means that either we are dividing by 0 perhaps, or possibly trying to go towards infinity, right? And that's technically called a discontinuity. So that, just like I said, that's how we can get there. One or more of the bounds are possibly infinite, right? That's one possibility. Or something within the bounds causes you to divide by 0. So in this case here, if we're trying to integrate from 0 to 4, that would perfectly fine to try. However, 3 makes this thing 0, so there's some sort of discontinuity happening within that graph that we need to account for. So how we do that with improper integrals, they can either converge or they can diverge, right? One or the other. If integrals converge, very simply, you get an answer, right? I mean, it might go on infinitely long, but maybe that infinitely long space kind of squeezes together enough that we can, pretty much say, yeah, if you go on and on forever, sure, you're constantly adding stuff, but it gets so tiny it doesn't really matter. So that's called a convergence when you would get a numerical answer, right? That's a convergence. If an integral diverges, then that means that all that little bit of adding and adding and adding, even though it's getting smaller and smaller and smaller, is too much, and the integral essentially becomes infinite, right? We're trying to add so much stuff, it explodes and becomes infinite, and that's called a divergent integral, right? And we can't really evaluate that, but that's what those are called. And to take care of these improper integrals, or the steps to kind of do that, is what we're going to do is, number one, we're just going to go ahead and evaluate the integral. We're going to figure out the equation part of that. And then we're going to use our ideas of limits to figure out whether it converges or diverges. Does it become a particular number, or does it shoot off to infinity, or perhaps negative infinity as well? So to look at some examples of those. Here is an example of an improper integral that will converge together. So again, here it is improper because we have something bounding towards infinity. And how we get this to work out, again, we would take this and we would just evaluate our integral in that case. So we need to integrate e to the negative x, which in this case would be negative e to the negative x, right, if we did that integral. And then here we want to make sure that this goes from 0 up to infinity, right? I mean, that's kind of what we're doing. And I get what I'm typing now is technically incorrect because it has an infinity in here and we can't evaluate infinity. We should already have the limit in there, but I'm going to pause on that. I'm going to say, nah, I'm going to wait to put that limit in there. So in this case here, we have our infinity on that one, right? So we have that in there. And then, so that's kind of step one. We've evaluated that integral. That's step one. And then step two is to convert these integrals into a limit. And so whenever we would need to essentially plug in infinity, or plug in something that would make the denominator 0, instead of plugging that number in, we're going to change that into a limit. So what we would do here is we would say, well, let's plug in infinity, which we can't really do. So what we would do is we'd say, well, we'll do the limit as x goes to infinity, right? That's what we're going to do first here. And we'll do that to the negative e to the negative x portion. Okay? And then we would subtract the rest of this, negative e to the negative 0, because we can actually plug in 0 and evaluate that, right? So that's basically step two, is anything that has the limit part, we would do that, and then we'd subtract here. And then we just evaluate. this part here, e to the 0 power is 1, so we're subtracting -1, so that's the same as doing +1. And then in this case here, the limit as e approaches that, well, e to the -infinity, we kind of think of an exponential function, goes up and up and up. And as we back up, we go to -infinity on that graph. And if you're not sure, we can always, look that back up. Now e to the x, and we go towards -infinity back this way, right? What's happening is we're essentially going towards 0. That's what happens with that e to the x. It goes towards 0. So back in here, we can say, yep, this whole thing becomes -0. So who cares? 0 plus 1, which equals 1. So that whole thing converges to 1, right? And what did we really find here? To what did we actually look for? Well, if we look at this, what we did was we took this, essentially this graph, right, or e to the -x. That's what we started with. Let's pull this over here so they're right next to each other. Started with e to the x, and we're doing the integral from 0 out to infinity on this graph. So we're going from 0 out to infinity here. And so what that means is we're looking for everything that is underneath here, right? We're adding everything up. We're summing all of this space up underneath here. And in fact, we're not doing all of that, right? We are only going from 0 out to infinity, right? We're kind of cutting this off. So what we're doing is trying to add up and find what's the area of all this red space, even if we go out forever and ever and ever. Notice there's a little bit of red space way out here. And that's essentially what we're finding. What is the area of all of this red space? Well, the thing is, if we added up all of this red space out there, it would be equal to 1. That's essentially what you're finding. What's the area underneath that curve? Because we're adding up lots and lots of little rectangles forever and ever and ever and ever, right? We're adding up infinitely small rectangles for an infinite amount of time, essentially in an improper integral. But that integral becomes 1. So let's look at another one that converges here. So this one we have the integral from 0 to infinity, 1 over x squared plus 1. We could use our idea with looking up our trig functions on there, because that's x squared over 1. U substitution won't work perfectly in here, so we could look that one up. And in fact, if you go in and look it up, we see that that is the arctangent function, right? The arctan of x in there. Okay, that's the integral of that one. And then we're going to be again in evaluating from 0 out to infinity, right? That's what we're going to be doing in there. So actually, I guess I don't need to rewrite that down, because we can just figure that out in this case. Yeah. And that's going to be our arctangent. We want to go from infinity to 0. Again, I can't plug in infinity, so that particular one we would have to make into a limit, right? We have to limit as x goes to infinity of the arctangent of x, and then we can subtract the arctangent of 0. Right? We can put those different things in, right? That's what we could have there. Okay. And then we would look at these pieces on there. We could evaluate this. The limit as x goes to infinity of the arctangent of x. Now, we might not be entirely sure of what that is immediately, but we can kind of figure that out. Because what we're saying is x is getting larger and larger and larger. Basically, we're making a right triangle where the opposite side is just continuing to get larger and larger and larger, right? That's essentially what's happening. So we're saying, what does that angle continue to get closer and closer and closer to, which that angle gets closer and closer to pi over 2 or 90 degrees, but we're in calculus always working with radians, so we'd say that's pi over 2 in that case. And then the arctangent of 0, you can check that in, throw it in your calculator. This becomes 0. Nothing super exciting on that part. So then this just becomes pi over 2 when that's all said and done, right? And if you weren't sure about this, the arctangent, arctangent of as it goes to infinity, what I would do is I would go back here, maybe turn that one off, and I'd just graph y equals arctan of x and see, okay, where is this thing going to, and then kind of maybe think back to our trig stuff and say, oh yeah, I suppose that's going towards pi over 2 in that case. That's what it's going towards as we extend out towards infinity there. So again, to look at, what did we actually do here? We took this function, right? We took this 1 over x squared plus 1, just to reiterate. And again, if this makes sense and you want to jump ahead, go for it. So we're taking this function, which looks kind of neat here, right? And we are evaluating this, all the stuff that is greater than 0. We're just doing that part, and we're keeping track of this purple stuff. We're adding up all this purple area as we go out towards infinity. And in fact, if we add up all of that stuff in there, we would get pi over 2. That would be that integral. Now, actually, I haven't tried this in here. So let's see if this will actually work in here. Integral from 0 to, let's see if decimals will do this. Infinity of 1 over x squared plus 1. Yes. Nah. Let's see, what is it warning? Limits of integration must be finite. So in this case, you can't quite use Desmos to help you out because Desmos will not do improper integrals because I can only do integrals with finite numbers. I'm going to guess that's what the way that they program it. Maybe they're doing, whether it's the tangent rule or midpoint rule or something like that, to evaluate some of those integrals in there. They're probably not doing a symbolic integration behind that. But that's a way, if you want to visualize, what's going on, that's the area that we are finding in there. And we find out that that area is pi over 2. Now, not every integral happens to converge. In fact, quite a few of them, if we try to do that, they will diverge, right? So let's take a look at this. Okay, we're going to look at 1 over x. So what we would be doing here is we would, instead of looking at 1 over x squared, I'll just duplicate that function here and turn one of them off. We're going to be looking at 1 over x. And actually, we're looking at stuff that's bigger than 1. So this, again, very similar shape. It starts here, starts to decrease, 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 and decrease. We're going to add up all the stuff underneath here and see, what does it all add up to? Does it add up to 1? Maybe it adds up to 2. I don't know. Maybe it looks a little bit, a little bit more than this one. I mean, but it just kind of looks like the same, but shifted over, I guess. Maybe it's a little taller there. We might think, well, sure, maybe this one works out too. It looks very similar. So I would go through my process. Again, I would do the integral of that, right? It's 1 over x. So I might think, oh, it's -1 add. And oh man, I got to divide by 0. Oh, whoops. 1 over x, that's natural log of x, right? And we should go from 1 up to infinity. That's what we're going to do here. And I'm going to take that. Again, we got an infinity. I can't just evaluate, so we do have to do a limit very technically. I understand too, like as you guys are going, as you guys are going through on this, if you don't put the limit every time, like obviously I get that. I'm trying to be as, proper as I can, being that, we're kind of learning this stuff. But if you don't put this in a limit form and you just kind of think through what that one's going to be, you think you plug in infinity, I understand that. Like that makes sense too. But here we should technically do a limit. Natural log of 1 is in fact 0. So this part would be subtracting 0, which isn't going to do anything. But the limit, the natural log, as it goes towards infinity, actually slowly keeps creeping up and up and up, which you can go and check that on Desmos if you need to. So actually, this whole part just becomes infinity minus 0, which is just infinite, right? I mean, subtracting 0 isn't going to do anything to that. And so here what we end up with is that this thing is infinitely large. which seems odd that we keep adding all of this and it's infinitely large, even though it looks almost the same as this one, which does converge. So we can't go quite just by the shape whether something's going to converge or not. We do need to go ahead and check that stuff out. So here we would just say, yeah, the integral diverges. That would be our final answer on there. Oops. So we would state that integral diverges. Yeah. So if you get an answer where you get infinity or negative infinity as well, integral diverges. Yeah. Some different things. I'm just going to go through some other examples here. Sometimes you might need to use LHOP rule, which is why we went over that last week. So like here, if I was trying to evaluate this, I would need to first evaluate the integral, which in this case, I would have to use integration by parts. So I might start with 1 minus x as my u, which means du is just dx because of the derivative here. But in fact, it will be negative, just being careful of that. And then our dv would be e to the negative x, which means that's negative e to the negative x when we integrate that part out. And then we would just put that all together. So here when we do that, that should be b times u. So I have 1 minus x. Oh boy, all this is going crazy. 1 minus x times e x. And in fact, that's negative because of the extra negative on there. And then we should subtract the integral still from 1 to infinity. And I guess we wouldn't need those bounds because we're evaluating the whole thing. And these both have double negatives in there, so those will cancel out. Negative x dx. We'll insert that right in there. So that's our evaluation so far. And then we'd evaluate this, which would be negative e to the negative x. So in fact, actually, I'm just going to get rid of the integral on there, and that will make that negative be positive. And that's all we have on that part. So now we'd go towards infinity. And this is one part on this one especially where it is important that we use limits in this case. I didn't like my picture, huh? Try again. All right, where this one's important that we use limits here. Because it's e to the negative x, we want to check that. So here, what I'd do is I would convert these to limits. I'd plug those pieces in. So first off, we would plug in our idea for a limit as x, oops. Limit as x goes to infinity of this stuff. And then what we would do is we would subtract all of this stuff as we plug in 1, which where we go through that would be negative 1 minus 1, e to the negative 1 plus e to the negative 1, right? Which we can evaluate this stuff out here. All of this is gone because it's worth 0, didn't need that one there, right? So we're ending that. So here we need to do this. Sometimes it's easier to think about, those negative values mean that it's really on the denominator. This is 1 over e to the x. So we can kind of look at those different things. I know I did a lot of simplifying in there, but you guys have the video to watch, or you could, get that this is e to the negative 1 in that case. And then here we can look at this. These two things, this one here, right, becomes 0 because if we let e get very, very large, the denominator pretty much gets really big, so this part becomes 0. And this one here is infinity over infinity, right? It's infinity over infinity, or actually, negative infinity, so those go away. So in this case, this part becomes 0. This part, we would take the derivative of that. So the derivative here would be negative 1, therefore canceling all of that stuff. and then the bottom still stays as e to the x, right? Because we use that LHOP rule on that, which now we can actually evaluate that this will also be 0 if we do that limit on there. And so the whole thing ends up becoming negative e to the -1 power, which seems a little bit odd. And I actually have to double check my notes. I don't remember why my negative popped up in there, but I'll look back at that in a little bit on there. Oops. Oh, yeah. Yep. Sorry, we'll take a look at why this is negative for a second there. I was like, why is that negative again? But yeah, I forgot what the shape of the graph looks like. So this thing, all said and done, if we want to look at this very nicely, is -1 over e. That's what that ends up becoming in there. And if we want to look at, why does that thing look the way it does, right? We say, well, we have this function, 1 minus x e to the -x. So I would again take this as 1 minus x e to the -x, right? And what we're trying to look at here oops, let's flip these around. Okay, so what we're looking at is from 1 to infinity. That's what we were doing there. And you can see the reason it's negative is because it's underneath the x-axis. So you get a negative result because it is underneath there. And so if we add up all this red stuff under here, we get a value of 1 over e, which, we could always use a calculator and figure out that that's all 0.36, yada, yada, yada. That's what the value is underneath that. So sometimes you can use LHOP to work that part out. That will sometimes pop up as well. All right, one final example that we'll go over here, and that's discontinuity within the integral. We might look at this and say, well, this is just fine. We evaluate it and plug our stuff in and go from there, right? But what we could notice here is if we try to plug in 3, it does not work on here. So we are going to have to use a limit in that case also. So on here, what we would do is we would evaluate this limit. Again, this is a -3/2 power. So we would, bring that up to a, -1/2 power in that case. So that'd be x minus 3 to the half, right? So I'm just going to put 0.5 because it doesn't let me do fractions super nice right now. So we bring that up to that -1/2 power and then divide by the -1/2, which would make that -2, right? In that case, and we are going to evaluate this thing from 3 to 4. So. Oh. Oh, that kind of looks about right. We'll leave it at that. Oh, it did do it right. I formatted it when I put it in. And then in here, again, we can't, we can't plug in 3 necessarily, so we do have to do a limit on that one. So first off, we can plug in 4, and that will be, negative. Well, actually, I can put the whole thing on just to emphasize that. -2 over 4 minus 3. 1/2, or the square root of that. So it's just going to be -2 all throughout here. And then what we will have to do is subtract the limit. And now we have to be a little bit careful in this point because we're approaching 3, but from the right. Yeah. So again, kind of going back to our idea of limits here, we got to approach from the right. And what I mean by that, if we look at what does that graph kind of look like, we're going from 1 over x minus 3 to the 3/2 power. We're approaching 3 from this right-hand side. We're trying to go from 4 up to 3 here. So we're approaching from this side. That's what we want to find on our limits. So we do have to put that's from the right on there. Okay. And then let's take out these pieces here because we don't need those either. Yeah. It's three approaches that. And so we can evaluate parts of these. I can evaluate some stuff out of here. I mean, as we talked about, this whole thing becomes -2, which is perfectly fine. Then here we have to think about, okay, what's happening here on the denominator, right? This is approaching 3 from the right, meaning that we're using stuff like 3.1 minus 3, okay? And then we're taking that square root of that stuff. And then we're taking 3.01 and 3.001. So this denominator, right, in fact, is getting kind of larger and larger and larger and larger, right, in that case. And so what's going to happen here is this whole thing is going to go to infinity, right? That's kind of what's happening there. And so it doesn't really matter. This -2 is not doing too much. This thing is going to diverge in this instance, right? That's what's going to happen here. Let's see if we can rearrange this so it looks a little nicer. So that's what would happen on this one here, is that this one actually ends up diverging as well. Okay. And that's what we would say on this one, is that this one diverges. So there's a few examples. These ones, can be a little bit difficult because of that weird limit stuff in there. So you guys have an attachment where you can put, your worker stuff, or, write it out, take a picture, and upload those as well. You guys have any other questions, send them my way and we'll get those figured out. See you later.